This is the third lecture in this course on AI. So, we were talking about some introductory things in AI. So, basically, you talk about AI systems as in this particular way, systems that think like human, systems that act like humans, systems that think rationally, or systems that act rationally. So these are the various possibilities that you can have basically. So how do you make an AI system that thinks like humans? How do you make a AI system that acts like humans? How do you make a AI system that thinks in a rational way? Okay. So let us see what are the differences between these. So when you talk about systems that think like humans, um, you need to automate the activities like the human being does. So when the human being perceives something, he does things like making decisions, carrying out problem solving, learning, etc. So all these things have to be automated and seen that the computer is able to do these things. Okay. So basically what you're trying to see how the brain functions and how it processes the information. So that is the area of cognitive science basically. Okay. So the cognitive processes manipulate representation to build new representations that are used to generate actions. So another thing is, how do you make systems that act like humans? So obviously you need to see the behavior of humans, and by observation you see how the human behaves, and then you find a computer which behaves and make the computer behave in the same way. So this, when you come to acting like humans, it will be something like the robotics part which we need to see there. And systems that think in a rational way. So what do you mean by rational? Okay, so it doesn't really need to think the way human beings think, so long as it gives the correct result. Okay, so the idea is that the you have to see what rationality basically is. So we will see a little later what you mean by rational. So it comes to a decision in a rational manner. Okay, so it uses things like logic, okay, to measure the correctness of something. Not all behavior are mediated by logical deliberations, basically, and systems that act rationally. So rational behavior means the computer is doing the right thing. So how do you find out whether it's doing the right thing? It's the performance metric which you need to see. So this is the present state of the art that we can say that we have, right? So you have robotic vehicles, that is vehicles which are unmanned, okay? So you have driverless robotic cars, okay, which have won some challenges and things, right? And you also have the CMU, some car which has won a challenge for driving safely among pedestrians, other vehicles, etc. Speech recognition, of course, to book a flight, you can talk with the speech recognition and dialogue system, right? Autonomous planning and scheduling, you have things like mission planning, planning of the space mission, right? So what it does is that it generates plans, okay, from the goals. So what are the goals that the spacecraft has to achieve, and from that you generate the plans, and it also carries out monitoring of the execution of these plans, and then you detect whether the plan is going well or not. If the plan is not going well, it actually recovers from the problem and continues from there, right? So these are some of the things that are basically available there. And game playing, okay, so you find that of course we just saw a little earlier that Deep Blue has defeated world champion Kasparov, right? And now it is actually convincingly defeating humans, the computers convincingly defeating. Spam classification and automatic detection is another very important aspect. Logistic planning, robotics. Okay, so in robotics, you have the Roomba, the vacuum cleaner, which for homes, right, by the iRobot Corporation. And they also use robots in hazardous conditions to deal with hazardous material, etc. Okay, explosives and all those type of things. So obviously, it's very helpful in such places, basically. Machine translation, you have very good machine translation programs nowadays. So this you could say is the present state of the art. So if we just go through what all we have gone through now, right, what we can say is that it's an interdisciplinary field, and there are a number of different areas, okay, in which we need to study over here, right? And it's very important as a knowledge-based system, the way you store knowledge and make use of knowledge. Uses non-monotonic reasoning, and you have number of commercial packages available, basically. So that gives a little bit of some introduction to artificial intelligence, and we'll continue now with what are called intelligent agents. Okay, in other words, what is an agent? An agent is a machine, okay, which carries out or acts according to the decision that it takes, right? So let us see what a intelligent agent is basically. So basically you can say that if you consider the environment, you have an agent which actually perceives the environment around it, right? And whenever there is a change in that environment, okay, so it senses that, and the agent will act upon the environment. So it will decide what is the action to take, and that action is carried out through the actuators, right? And an action is taken in the environment. So this is what you call an agent, basically. Okay, so if you look at a human agent, so a human being, you can consider them as human agents. And what is the input to the human agent? You sense things through your ears, your eyes, and other organs, right? As the sensors. And as actuators, we use legs, hands, voice, all these type of things. But if you take a robotic agent, it has things like camera, infrared range finders, and other sensors, right, as the input. And as the output actuators, you have various motors, right, which act as the actuators. So the input which is coming into the agent from the environment is known as the percept. Okay, so percept is the perceptual input which comes into the agent. And if you take all the percepts which come into the agent, okay, right from before, okay, you have a sequence of percepts, okay. So a percept sequence is the history of everything that the agent has perceived till this point in time. So that is known as the percept sequence. And the agent has to look at the percept sequence and then decide what is the action to be taken for that. So you have what is known as a agent function, which maps the percept sequence to the percept behavior, to an action, basically. One method of doing that is what is known as the table lookup. Okay, so let us see what is it. So here you can see you have the agent and the environment, right? And the effectors and the sensors. Sensors are used as input and effectors are used as for actions. Okay, so if we take the vacuum cleaner, okay, you can see, for example, you have a system here where you have two rooms A and B, where you may have dirt or you may not have dirt, and you have one vacuum cleaner, right, which can be either an A or it can be B. So there will be certain actions that it can take. Okay, so the actions that it can take are right, left, and suck. Right. So if you have a percept sequence like this, okay, so suppose you have A clean, which means it's in A and A is clean. So what is the action to be taken? It should go right, right? Suppose it's in A and A is dirty, the action that it should take is suck the dirt. So this is like an example of a table lookup basically. Okay, so when we say agent behaves in a rational manner, what does it mean? It means that it does the right thing. Okay, so what do you mean by right thing? It is what is desirable at that point in time. Okay, so the sequence of actions done by the agent at that time is desirable. Okay, so that's what you mean by rationality, and usually you have a performance measure which evaluates the desirability of an action. Okay, and the performance measures are designed according to what one wants in the environment. Okay, it's not part of the agent, the performance measure. Okay. Okay, so what is rational at a particular given time depends on all these factors. The performance measure, right, that defines a criterion of success, the agent's prior knowledge of the environment. Okay. Third is the actions that the agent can perform. Okay, so it has to be one of the actions that the agent can perform. Okay, so it is constrained by that, and the agent's percept sequence to date. So how do we define a rational agent? For each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure given the evidence provided by the percept sequence and whatever built-in knowledge the agent has. So this is what we mean by a rational agent basically. Okay. Now if we look at an agent, you have what is called autonomy, right? Does it have autonomy or not? Okay. So when you say an agent has autonomy, it means that it's able to change itself or evolve according to the environment. If it's not able to do that, then it does not have autonomy. Okay. For example, if we take a clock, okay, so if you look at the clock as an agent, okay, so it has some inbuilt knowledge in it saying that you need to move this much, every second you need to move, etc. Right? Now what happens is that it's not able to perceive the environment. All it does is it just keeps moving according to the built-in knowledge that it has from before. So it doesn't really have any autonomy. Now if it is able to sense, for example, if you take the same clock to say America, the time is going to change, right? But it's not able to do that automatically because it lacks that autonomy, right? So autonomy is that it actually evolves. Okay. So what you find is most agents, they will have some inbuilt knowledge at the beginning, right? But what it does is that by perceiving the environment, it evolves, okay, and it learns from that. Okay, so an agent which can learn from the environment is known as an autonomous agent, or one which has more autonomy. So the incorporation of learning allows one to design a rational agent that will succeed in any type of environment, right? So it evolves depending on the environment. That's what we mean by autonomy basically, okay? So now when we have a task which needs to be performed, okay, so it depends on all these factors, okay. One is the performance measure. So what is the performance measure that is being used? What is the type of environment that you have? The actuators and the sensors, right? Actuator is the output. What is the output that you expect? And sensors are the input. What is the input? For example, if you have a taxi driver agent, okay, so for example, if you have a car which is moving in the traffic, right? What is the performance measure that you would use there, okay? The I mean, the journey should be safe, it should be fast, it should be legal, it should be a comfortable trip, it should maximize profits, okay, it should use less petrol, whatever, right? So these type of things form your performance measure. What is the environment? The environment consists of the road, it consists of other traffic along on the roads, other vehicles, pedestrians, customers, all these things. What is the actuator? What is the output that you want the taxi to do? So it should be, there'll be things like steering, accelerator, braking, um, horn, display, all these type of things. And what is the sensors used here? The cameras, the sonar, speedometer, odometer, accelerator, all these type of things. So whenever you have any task, okay, you need to specify these four, which is called P's, right? So these are the four that need to be specified. So here we have given a number of agents, okay, and specified the P's for those, right? Let us take one or two here. So if we take medical diagnosis system, right? So in the medical diagnosis system, what is the performance metric? We need a healthy patient, reduce costs, etc. And the environment is the patient, the hospital, the staff, the nurse, nurses, all those things, right? Doctors. And what is the actuators, or what is the output we want? Questions which you have to ask the patient, the tests which need to be done, the diagnosis, treatment, the referral to other doctors, all these are the output. And the inputs will be symptoms from the patient, okay, patient's answers, what are the symptoms that the patient has, finding of tests, all those type of things. So if we look at interactive English tutor, the students score on the tests, right? That's the performance metric. You want the student to get the highest score possible. And the environment will be the test questions, the students, all those type of things. And what should be the output? Display of exercises, suggestions, corrections, etc. And key input will be the keyboard entry done by the student basically, right? So these would be the, what do you mean by P's? And then we look at the environment, right? So the environment has certain properties. So let us look at the environment. So the environment may be fully observable or partially observable, may be single agent, multiple agent, deterministic or stochastic, episodic or sequential, discrete or continuous, known or unknown, right? So if we look at the properties of task environments, first, fully observable versus partially observable. In some cases, the environment is fully observable. For example, if we take a chess game, right? So if you have a computer playing a chess game, the computer is knowing fully the environment which it requires, okay, to carry out its action. Okay, in other words, it knows the position of all the pawns, everything of itself as well as the opponents. Okay. If you look at the taxi driver in the taxi environment, it's not fully aware of the environment, only of that part of the environment around it, depending on the sensors that it has, right? So that is actually only partially observable. Okay. Now if you look at the vacuum cleaner agent, it may not be aware of the entire set of rooms, right? It may be only knowing what is the dirt, whether dirt is there in that particular room or not. It may not know what happens in the other rooms. So again, that would be partially observable. So it's possible that in some cases it's only partially observable. For example, if you have an agent which is playing some card game or something, it may be aware only of its own cards, okay, and it may be aware of what the other person, the card that the other person puts down, okay, but it may not be it may not be fully observable, the environment. So that is what we mean by that. Next is whether it's a single agent or a multi-agent. Okay, so possibly if you have many agents working simultaneously, okay, an agent actually sees that its own performance metric improves, whereas other agent performance metric come down. Okay, if that's the case, then you say that these are competitive agents. Okay, but if you have two agents such that if one's performance improves, the other's performance also improves, then you call them as cooperative agents basically. Okay, so it's possible that you are working in a scenario with multiple agents, or you may be working in a scenario with just one agent, right? You can have, for example, one computer working with one person, right? So that would be like a single agent. Now the environment may be deterministic or stochastic. In other words, once the agent sees what the environment is and is going to decide what's the next action to take, the environment remains deterministic. That means it doesn't change, right? But if it changes even during that time, it's known as stochastic. For example, in the taxi driving, we don't know about the behavior of other cars or other people on the road, etc. Okay, so before, suppose the agent sees what is in the environment and is deciding what action to take, during that time also the environment can change. Okay, so it is stochastic. Whereas if you take chess, okay, so once the other person has made a move and you are waiting to make the move yourself, there is no change in the environment. So you call that as a deterministic agent or environment, right? Now episodal versus sequential. In an episodic agent, for example, if you take any classification task, one decision which is taken does not affect the next one. Okay. For example, an agent that has to spot a defective part in the assembly line. Okay, once it makes a decision on one part, it does not have any bearing on the other part. Okay, so those things are known as episodic, and in chess, etc., the once a move is made, it actually influences all the moves that are made later. Okay, so you call such things as sequential basically. So episodic environments are easier to work with. Discrete versus continuous. In taxi driving, it is continuous, right? So everything keeps changing in a continuous manner. Okay. Whereas in chess, it has a finite number of discrete moves that are possible, right? So that is discrete. So there are only so many moves possible and all of them are discrete. Okay. Whereas in the case of taxi driving, it's a continuous state, which makes it more difficult basically. Okay. Known versus unknown. So if it is a known environment, the outcome for all actions are known to you. Okay, so you know if you take this action, this is going to happen. If you take this action, this is going to happen. But if the environment is totally unknown, right, then it becomes more difficult to take decisions. Okay. You can have an unknown environment, but it can be fully observable also. But because it is unknown, okay, you don't know what to do at that point in time. Okay. So here we have a number of different tasks here. Okay. So we have given, for example, if you take a crossword puzzle agent, okay, it's fully observable. It's a single agent, deterministic, because there are deterministic number of mu's. Sequential, because if you enter one word, it changes the next word also, right? And it is static and discrete. Okay, so for example, if we take a taxi driver, it's partially observable, multi-agent, stochastic, sequential, dynamic and continuous. Okay. So what you find is the hardest case is something is partially observable, multi-agent, stochastic, sequential, dynamic and continuous, okay, and unknown. Okay, so many times it's unknown. Okay, if you take an action, what happens? So these are something like the taxi driving. That will be the hardest environment that you can have, right? So if you know what is the nature of your environment, it will help you to decide what are the actions to be taken basically. Okay. So now if we look at agents, okay, so what you do is you design an agent program, okay, which implements the agent function. So what does the agent function do? It does the mapping from the percept sequence to the action that is to be taken. Okay. So the program runs on a computer system with sensors and actuations, which is the architecture of the system. So you can say your agent consists of the architecture plus the program which you have. Okay. So this is like a table driven agent. Okay. So in a table driven agent, the input is the percept. Okay. And the output you get is the action that you are going to take. So you append the percept to the percept sequence, right? And you look up in the lookup table. So if this is the percept sequence in the table, this is the action to be taken and you return that particular action. So this is the table driven function. Okay. The problem with the table driven agent is that the percept sequence keeps on increasing, right? The percept sequence, when it increases, it's very difficult to solve this problem with the lookup table because the lookup table will become very big, right? So what does it mean when you have a very big table? Even in chess you would have 10 to the power of 150 entries, okay, because there are 75 moves done by each agent, okay, or each person, that is 150 moves. So the percept sequences that you can have is 10 to the power of 150. So what happens when the size of the table becomes big? No physical agent will have the space to store the table. The designer wouldn't have time to create the table. No agent would ever learn the right table entries from its experience. And the designer has no guidance about how to fill in the table entries, right? So these are some problems with the table driven type of agent. It can be used only in very minor places, okay. So basically there are 4 types of agents that we will consider here. The first one is what is called the simple reflex agent. Second one is the model based reflex agent, the goal based agent, and the utility based agent. Okay, so these are the 4 types of agents that we are going to see here. So if you take the simple reflex agent, it does not look at the percept sequence, okay, but only on the percept at that particular point in time, okay, and then it has the condition action rule, something like a table lookup, right? So it decides if this is the percept, this is the action to be taken, okay, if this is the percept, this is the action to be taken, okay. So this simplifies things because you are only looking at the percept at this particular point in time, okay. So this is your percept, I mean condition action rules, okay. You have the environment here, what the world is like, and then you decide what is the action to take now, right. So this is the simple reflex agent, okay. So you come up with what is called a state depending on the percept, okay, and you find the rule by taking the state and carrying out the rule matching, and you get the rule and you use that rule to decide on what action is to be taken basically. Okay, then we come to the model based reflex agent. So the model based reflex agent keeps track of the world, okay, and it maintains an internal state which depends on the percept history, and updating the internal state depends on information of how the world evolves as well as on the agent's own action. Okay, so these two are used to update the state. Okay, so here we have the environment, and this is how the world is like now. Okay, how the world evolves is used over there, and what your action does to it, and the state. Okay, so this is used along with the condition action rules to get the output. So here we can see that using the state, present state, and using the previous state and the percept and the model and the action that was taken previously, you are updating the state. Okay, and this state is used to find the rule and the action which needs to be taken at the next point in time, basically. And goal based agent actually uses information about the goal. What is the goal of this agent? Okay, what is it that this agent wants to do? Okay, so it uses search, planning, all these things. Okay, so here you find that it uses the goals and uses these goals to decide what is the action to be taken, basically. Okay, utility based agents, like I said, uses utilities, not only goals. Okay, for example, if you use only goals, there may be many actions which can be taken to get a particular goal, right? For example, if you want to move from one point to another point, there may be various different routes which you can take, right? All of them will achieve the goal that you want, but you need to also use the utility. Okay, you want a quicker route, you want a safer route, more reliable route, cheaper route, etc., right? So what you use is what is called the utility measure, and the utility measure will tell you which action to take at a particular point in time. So here you use the utility. How happy am I? How happy will I be if I take this particular action? So that is used as a utility to decide what action is to be taken, basically. Okay, so here we have a model of a learning agent. So what are the different parts of this? You have the sensor, and you have a performance standard which is outside the agent, basically, and you have a critic which gives feedback on how the performance standard is met or not. Then you have a learning agent which actually does the learning part, okay, and gives recommendations to the performance element. And you have the problem generator which keeps generating new ways of solving the problem. Okay, so here we can see you have the learning agent which makes improvements. Learning mechanism can be used to improve every part of the agent. Then you have a performance element, okay, which selects external actions. Critic tells the learning agent how well the agent is doing using a performance standard, and the problem generator suggests action which may lead to new and informative experiences, right? So this is the what you would call the model of a learning agent which is used nowadays, right, as an agent. So you can say agent actually looks like this, right? So we can see the many things that can be used over here. For example, we can see here that when you say the learning element makes improvement, etc., it carries out, it uses different learning algorithms, right, over there for improvement. And when you say problem generator suggests actions which lead to new and informative experiences, it keeps trying out new novel ways of solving the problem, right? So all these things use, the general things like learning, etc., which we talk about. Okay, so here we'll stop this particular session. Uh, so we will continue the next thing, which is problem solving, in the next session. Thank you.